Knee pain is common, but what if we could detect the early signs of osteoarthritis before the damage gets worse? Our thesis introduces a smarter way to screen for OA, using thermal imaging and artificial intelligence. Every day, millions of people suffer from knee pain, a discomfort that slowly turns into something more serious. But by the time osteoarthritis is diagnosed, it's often too late. You see, traditional methods like X-rays usually detect osteoarthritis at later stages, when the joint space has already narrowed, when bone spurs have already formed, when damage is already done.
The core of our prototype is the Raspberry Pi 5. It acts as the central processing unit, managing data from the thermal camera and handling image capture in real time. The Raspberry Pi 5 processes temperature data, overlays it onto a visual display, and stores it locally or streams it to an external device. Its speed and compact design make it ideal for portable, low-power applications like ours, bringing reliable performance to our thermal imaging system. The new leptin is known as the FLIR leptin 2.5 with radiometry. Compared to the old model, they both have a resolution of 80 by 60 pixels and can see in the 8 to 14 micrometer wavelength range. The new leptin has a slightly decreased field of view at 50 degrees. Both have a pretty good sensitivity at under 50 millikelvin, which allows us to more easily identify objects in a scene. The frame rate is fairly slow, often under 9 frames per second. But this is still quite fast if you're looking to measure several temperature values in a scene. You control the camera over an I2C interface, and you can get video and temperature data over SPI. Note that FLIR promises a time of under 0.5 seconds to process an image for the original camera and under 1.2 seconds for the new one. In reality, I saw the lag time being well under half a second for the new leptin. One of the biggest additions in the leptin 2.5 is the integrated shutter. The shutter periodically blocks out radiation from the sensor to allow for internal corrections to occur, thus improving image quality. FLIR's marketing team wants you to think that the new model has radiometry and the old one doesn't. When it comes to these camera modules, radiometry just refers to the fact that the device can internally adjust the data so that it's not affected by the camera's own temperature. As it turns out, both old and new modules are capable of this adjustment. The new 2.5 model is just also capable of sending data in Kelvin, saving you some processing time and converting raw pixel values. Both cameras draw a fairly low power.
The process begins with the startup of the Raspberry Pi 5 and running the Visual Studio Code software. There are 5 buttons one can interact with. The first one is storage, where all the data captured by the thermal camera will be saved and stored. You can also create your own folder so that you can organize and label each data captured. Next is notes, where you can jot down notes if needed. For example, like how many captures have been made for one patient, or what side of knee have been captured.
About is the section where you can find more information about the device.
Display is where you can see the image in real time and have the option to capture the image. Next is Run Inference, where the captured image will be selected and be processed by the CNN and will give result based on KL scale. Let's now demonstrate the device in action, capturing a real thermal image and processing it through the system to see if it performs as expected. And based on the result, it did.